Hello everyone, welcome to our class ECE 221, Communications 1, Principles of Communications. Before we begin, please allow me to briefly introduce to you myself. I am Engineer Handel de la Serna Magnanao, so you can call me Sir Dill. So I am a Master of Engineering in Telecommunications graduate. I did it in year 2000 at the Asian Institute of Technology in Thailand. And I also have 42 units in Master of Science in Teaching Mathematics. Uh, I did it at the University of Cebu in 1997. And I also finished two Bachelor of Science in Engineering courses, Electrical Engineering and also Electronics and Communications Engineering. Both were from the Cebu Institute of Technology and now called Cebu Institute of Technology University, Cebu City, Philippines in 1992. Okay, so welcome once again to our class. This time we are going to talk about principles of communication systems. So we have two very nice reference books, Electronics Communication System by Kennedy and Davis, Electronics Communication System by Wayne Tomasi. So you can use either of this or both of these reference book for this course. All right, so here are the objectives of our discussion for today. At the end of the course or at the end of the discussions, the students will be able to understand and describe the basic elements of a communication system that is composed of transmitter, receiver, noise, communication channel, or medium. Then do some basic calculations for the wavelength in the given electromagnetic frequency spectrum. So here are the contents of our discussion for today. So we'll talk about the introduction of the principles of communications. Then we'll talk about amplitude modulation, angle modulation, radio receivers, pulse modulation, digital transmission, multiplexing, line codes, and their spectra. So perhaps we can cover most of these topics for today, and the rest will be discussed in our other coming videos. Okay, for the introduction, so we'll talk about elements of the communication system, modulation and demodulation, noise in the communication system, signal to noise ratio, noise factor and noise figure, equivalent noise temperature. So perhaps three of them will be discussed today, and the rest will be in our future discussions. The electronic communication system. So what is its purpose, class? So the purpose of this electronic communication system is to communicate information between two or more locations commonly called stations. This is done by converting the original information into electromagnetic energy and then transmitting it to one or more receive stations where it is converted back to its original form. Okay, so that's its purpose. So the electronic communication system includes the following modules. We have the transmitter, transmission medium, a receiver, and a system noise. Okay, so it's shown here in this black diagram. So we have the transmitter, transmission medium or communication channel, and we have the receiver. So on this part, we have the information source, or we call it intelligence. And for this part, we have it can be a physical facility like a metallic or optical fiber cable or coaxial cable, or it could be a free space, that is the Earth's atmosphere. So this is where the system noise and interference will get in. Then at the receiver, we have here the received information. So this is the simplified block diagram of an electronic communication system. Okay, so in a little more details. So on the transmitter side, so we have the following uh, items here. We have the information source, input transducer, and we have the amplifier, modulator, then we have the transmitting antenna, and we have the channel where the noise will get in, and then we have the receiving antenna, then the modulator, detector, amplifier, output transducer, and information source. Okay, so the information source could be a voice, a picture, whatever, and it will be input to the transducer, which converts the analog signal into an electrical signal, and this will be amplified, and this will be modulated. The signal will be modulated, meaning it will be combined with the carrier frequency, and before it will be sent to the radiating antenna, it will radiate or propagate the signal that contains the carrier and also the information, and it will be received by the receiving antenna, and here it will be demodulated, so taking out or removing the information from the carrier. It will be detected by this detector, and it will be amplified, and then this will be an electrical signal then converted into output transducer, that which turns the electrical signal into the something that is like the information source, like the intelligence or the information. All right. So transmitter in the block diagram that have been shown a while ago. So transmitter is a collection of one or more electronic devices or circuits that converts the original source information to a form more suitable for transmission over a particular transmission medium. Right? So here's an example of the transmitter, radio transmitter. This is done by Guglielmo Marconi in the time of Guglielmo Marconi, 1901. So this is the first transatlantic radio transmitter. And here's some details about this transmitter, so you may read yourself. And as you can see here, very simple circuitry compared to the modern transmitter. So this is an example of the homemade long-range 1 watt FM radio transmitter circuit. Okay, so you can find it here from this link. Okay, so from the block diagram of electronic communication system, so we have the transmission medium, or we call it communication channel. So the purpose or the transmission medium or communication channel provides a means of transporting signals between the transmitter and receiver, and these are the types of medium that will be used or that can be used. We have the copper wire, we have the microwave, radio, satellite, optical fiber communication system, or it can have even the twisted pair wire or the coaxial cable. So these are some illustrations of some figures that show us the transmission medium, like the microwave, the transmitter, receiver. This is a medium. There's a radio wave, or something like this. Or it can be the cable. It can be transmission cables or fiber optic cable. In terms of electromagnetic frequency, something like this. Or it can be the satellite frequency for satellite transmissions. We have the uplink. We have here the transponder. So transmit and respond, not transponder. That's the meaning of transponder. So we have what we call transponder here. The purpose is to receive the signal from the Earth, then transmit back to Earth. So there will be amplifying processing here, because the signal from the Earth, because satellite is for the geostationary satellite, It's 36 kilometers from the ground. So naturally, the signal from here, from the ground, when it reaches there, that's very weak already. So it will be amplified and then send it back or reflect it back to the Earth. Okay, so in the communication channel, so we have what we call system noise. So it is any unwanted electrical signals that interfere with the information signal. So we'll give you the details of this part in our future discussions. And receiver, it is a collection of electronic devices and circuits that accepts the transmitted signals from the transmission medium and then converts those signals back to their original form. Okay, so here's some typical communication system where we have the input transducer, transmitter, then the transmission channel. We have here the receiver, then the output transducer. Okay, so one example is we have here a camera. There's a person here shooting this camera shooting this person, and then can be a digital or analog. Okay, and then the image here, the voice will be converted into electrical signal, and then it will be processed here. We have the modulation process happens here, and then sent to the satellite. And the signal is weak. It will be amplified and then sent back to Earth to the destination uh, receiving antenna. Then there will be a satellite box here that will do the demodulation. And then we have the TV monitor where you can see the image and hear the voice as what has been sent from the source. Or it can be a phonograph. We have here something like a music, then input to the transducer. Okay, this is the voice here or the music here. And we have the sample example transducer is a microphone, for example. Here, the transducer here is the camera, and then the voice signal will be converted into electrical signal, and it will be amplified. We have the phonograph scribe. Okay, it will be scribed here, recorded here, records done here. Then will be this will be a track. And there will be a track at this part here, and then records. Signal will be sent. No? Okay, and then we have records here, brought here, then the playback, the amplifier, and then you can hear the music, the voice through these speakers. Okay, so this is the simple logic about communication system class. Then we have what we call modulation and demodulation. So what is modulation and demodulation is all about? As it is impractical to propagate information signals over standard transmission media, it is often necessary to modulate the source information onto a higher frequency analog signal called carrier. The carrier signal carried or carries. No? This is carries. So the carrier signal carries the information or carry the this is S carries the information through the system. So information signal modulates the carrier by changing either its amplitude, frequency, or phase. Yeah. The information signal modulates the carrier by changing either its amplitude, frequency, or phase. So modulation. So what is modulation? Modulation is the process of changing one or more properties of the analog carrier in proportion with the information signal. So types of electronic communication system, we have analog. So in the system, energy is transmitted and received in analog form. That is a continuously varying signal such as sine wave. So sine wave is example of analog signal. Okay, so this is a sine wave. So both the information and carrier signals are analog signals. Okay, so for analog system. So both information and carrier signal are analog signals. Then for digital, it includes a broad range of communication techniques like digital transmission and digital radio. So digital transmission, it is a true digital system where digital pulses are transferred between two or more points in a communication system. True digital system where digital pulses. So what are digital pulses? So digital pulses class looks like this. So that's interpreted as 1. This is 0. This is 1, 0, and so on. Okay, so these are sample of digital pulses. So there is no analog carrier, and the original source information may be in digital or analog form. So if it is in analog form, it must be converted to digital pulses. Okay, so digital pulses, something like this, prior to transmission and converted back to analog form at the end or the receive end. So this requires physical facility between the transmitter and receiver, like a metallic wire, or it can be an optical fiber cable. Then we have what we call digital radio. So it is a transmission of digitally modulated analog carriers between two or more points in a communication system. So the modulating signal and the demodulated signal are digital pulses. So both of them digital pulses. So the digital pulses could originate from a digital transmission system or from digital source like computer, or it can be from binary encoded analog signal. Digital pulses modulate an analog carrier. So therefore, the transmission medium may be physical facility or free space. That is the Earth's atmosphere. So type of modulation, we have amplitude modulation, frequency modulation, and phase modulation. So if the information signal is analog, and if the amplitude V of the carrier is varied proportional to the information signal, then we have what we call amplitude modulation. So this will be the result, or this will be produced when amplitude of the carrier is varied according to the information of the signal. If the frequency F is varied proportional to the information signal, so we have what we call frequency modulation, or FM, that will be produced. And now if the phase or angle is varied proportional to the information signal, then we have what we call phase modulation. Okay, so these are the types of modulations, or type of modulation. So we have here in this equation class from our reference book, that is from 1-A. So we have this equation. So this is V of t equal to V sine of 2 pi ft plus theta. So where V of t here is the time varying sine wave voltage, meaning it goes up or down, it rises or go down with respect to time. So it varies. No? It's sinusoidal. It's analog. So V is the peak amplitude volts. This one. This is the peak amplitude. The unit is in volts. And F is the frequency. The unit is in hertz. Theta, a phase shift. The unit is in radians, or that is the angle, phase shift angle. So a summary of various modulation techniques is shown here. So we have here the modulating signal, that is analog. So we have AM, FM, PM, where we have the general equation of the time varying sine wave. Okay, so digitally we have ESK, FSK, and PSK. A means amplitude, S means shift, K is keying. So amplitude shift keying, frequency shift keying, phase shift keying, and we have here QAM, meaning the quadrature amplitude modulation. Okay, so these are the forms of digital modulation: ES key, IF key, PS key, and QAM. So amplitude shift keying. So what is this? So if the information signal is digital and the amplitude V of the carrier is varied proportional to the information signal, a digitally modulated signal is known as amplitude shift keying. Okay, so remember, if the information signal is digital, okay, information signal is digital, meaning in terms of pulses or maybe 0 or 1, and the amplitude V of the carrier is varied proportional to the information signal, then a digitally modulated signal is known as the amplitude shift keying. Then for the frequency shift keying, if the frequency F is varied proportional to the information signal, then the frequency shift keying will be produced. Or if the phase angle is varied proportional to the information signal, then we have what we call phase shift keying or PSK. So this will be produced in this process. Then quadrature amplitude modulation. This time we have both. No? We have both. If both the amplitude and the phase are varied proportional to the information signal, then we have what we call quadrature amplitude modulation. So this is the result of varying, no? Variation of both the amplitude and the phase. Modulator, modulated signal, demodulation. So modulator. So modulation is performed in a transmitter by a circuit called modulator. So it is a way of making the information ride the carrier or combining the information and the carrier. So that is modulation. Then the result will be the modulated wave. So a carrier that has been acted on by an information signal is called a modulated wave or modulated signal. Then for demodulation, it is the reverse process of modulation and converts the modulated carrier back to the original information. So that is removing the information from the carrier. All right. So it's just like, for example, you ride your car. So your car is the carrier. You are the information, and you travel a certain distance. When you reach the destination, you get out from the car. Okay, so you are separating from your car now. So the first process, you ride a car, so that is what we call modulation. And when you travel with the car, so that is the transmission. And then when you reach the destination and you get out from the car, so that is demodulation. You're removing yourself from the car. So that is demodulation, removing the information from the carrier frequency. So demodulation is performed in a receiver by a circuit called demodulator. Okay, so modulation and demodulation. So why use modulation? So here are some reasons why we use modulation. So carrying one signal on another. So that is modulation. Carrying one signal on another, or making the information ride in a carrier frequency. So use carrier. So modulated carrier transmitted. So it is the modulated carrier that will be transmitted because it is easier to transmit frequencies that is higher than the information signal. Problems with transmitting baseband signal. Okay, there will be problems with transmitting baseband signal, so we need a carrier to do it. So antenna is difficult. This is the reason. No? Problems with transmitting baseband signal means that antenna difficult at low frequencies. So it's difficult to transmit low frequencies using the antenna. So noise and interference at low frequencies is very high, very high. So can't share with others. That's a problem. Then easier to transmit carrier at higher frequency and can choose convenient frequency. All right. Then antenna can be smaller. So that's what one good thing, no? To transmit higher frequency, antenna is smaller. Then maybe useful propagation effects. So fractional bandwidth much smaller. All right. Then antennas and other components easier to design. Can have many frequency channel. Okay, so that's the reason why we use modulation class. So why modulation is necessary? So it is extremely difficult to radiate low frequency signals from an antenna. So by the way, this is from an antenna in the form of electromagnetic energy. Okay, it is extremely difficult to radiate low frequency signals. Information signal often occupy the same frequency band, and if signals from two or more sources are transmitted at the same time, they would interfere with each other. So that's one problem in sending a low frequency signal. For example, all commercial FM broadcasts voice and music signals that occupies the audio frequency band from approximately 300 Hz to 15 kHz. That is for all commercial FM. So to avoid interfering with each other, each station converts its information to a different frequency band or channel. And the term channel is often used to refer to a specific band of frequencies allocated a particular service. Then a standard voice band channel occupies approximately a 3 kHz bandwidth and is used for transmission of voice quality signals. Like for example, commercial AM broadcast channels occupy approximately a 10 kHz frequency band, and a 30 MHz or more bandwidth is required for microwave and satellite radio channels. Okay, so that's why it's too expensive class. The frequency is too expensive because of the very limited space, limited space. So for radio transmission, so what is radio? So radio, the wireless transmission through space of electromagnetic waves in the approximate frequency range from 10 kilohertz to 300,000 megahertz. So that is what we call radio. So these are called radio frequencies. Now here's the analog electronic communication system. So this is a little detailed representation of what we had at the beginning. So we have here the low frequency source, that is the information. It can be analog or digital. And we have the high frequency oscillator. Okay, so this is a single frequency carrier signal injected to this part of the system and combine with the information. So modulator and frequency up converter. So modulate the uh, information or modulate the frequency with this information. At the same time, uh, up converter means the frequency will be converted. So the result here, the modulated wave could be the difference, the sum, and also the product. Okay. Then we have here the power amplifier. So to amplify the modulated wave and then transmit through the communication channel, okay, or through transmission medium, and then at the receiving end it will be amplified, and then the modulated signal will be down converted. The frequency is down converted by the frequency down converter. Okay, there is also a local oscillator here that will be combined with where the frequency is combined with a modulated wave to give us again the modulated wave here. And at this point, this will be demodulated. It means to separate the signal, the information from the carrier frequency. Alright, so information signal or intelligence signals, it combines with the carrier in the modulator to produce a modulated wave. So that's the explanation of this black. And then the information can be in analog or digital form, and the modulator can perform either analog or digital modulation. Information signals are up converted from low frequencies to high frequencies in the transmitter side, and down converted from the high frequency to low frequency in the receiving side. Now we have what we call frequency translation. So this is the process of converting a frequency or band of frequencies to another location in the total frequency spectrum. This is called frequency translation. Okay, so that's frequency translation. Then the modulated signal is transported to the receiver over a transmission system. If the receiver or in the receiver, the modulated signal is amplified, down converted in frequency, and then demodulated to reproduce the signal source information. So the electromagnetic energy can propagate as a voltage or current along a metallic wire, as emitted radio waves through free space, or as light waves down an optical fiber. It is distributed throughout an almost infinite range of frequencies. So when we speak of frequencies, it is the number of times a periodic motion, such as a sine wave. Now we have a sine wave. So sine wave is something like this. So periodic motion. Okay. So that's an example of a sine wave. So the sine wave of voltage or current occurs in a given period of time. So its complete alternation of the waveform is called cycle. So it means, class, this is what we call cycle, one cycle. Okay, this is a cycle. This is one cycle, one period. So its complete alternation of the waveform is called cycle. So the basic unit of frequency is hertz. So if this one cycle happens in 1 second, for example, this period is 1 second, the period is 1 second, one cycle is 1 second. So we have what we call hertz. So if this is in 1 second, so if the cycle happens in 1 second, then we have what we call hertz frequency. So every cycle here is 1 second, so we have what we call hertz, the frequency of this cycle occurs. Okay, so 1 hertz is equal to 1 cycle per second. So that is 1 hertz. Then we have what we call transmission frequencies. So the useful electromagnetic frequency spectrum extends from approximately 10 kilohertz to several billions of hertz. So the lowest frequencies are used only for applications like communicating in water. So this is the lowest frequencies. So that is the one that is used in sonar. Electromagnetic frequency spectrum, it is divided into subsections or bands, with each band having a different name and boundary. So the International Telecommunications Union, or ITU, is an international agency in control of allocating frequencies and services within the overall frequency spectrum. So this is the one that is responsible in assigning frequencies in any country. In the United States, the Federal Communication Commission, FCC, assigns frequencies and communication services for free space radio propagation. For example, the commercial FM broadcast band has been assigned to 88 megahertz to 108 megahertz. So if you're asked to find the bandwidth, what is the bandwidth We abbreviate the bandwidth as this. So that is just the difference of the higher minus lower, which is eta. So the bandwidth is, that is 20. That is 20 megahertz. So that is the bandwidth of the FM, no, frequency modulation station. All right. So here's the electromagnetic frequency spectrum. So the reading here is from left to right. No? From left to right, so the frequency is increasing. So we have here 10 to the 0 means 1, 10 to the 1 is 10, 10 to the 2 is 100, 10 to 3 is 1000, 10 to 4 is 10,000, 10 to 5 is 100,000, 10 to 6 is 1 million, 1 million hertz. So the unit here is in hertz. So the television, so this is what we call radio frequency band. Radio frequency band ranges from this, okay, and also to this. Then after that, we have another band here, the optical fiber band, okay, covering this frequency. Then we have the X-rays, we have the gamma rays, and then the cosmic rays. So cosmic rays is the highest frequency, 10 to the 22. Okay. Okay, so this is the electromagnetic frequency spectrum. So another way of looking at this electromagnetic frequency spectrum is something like this. Now this is the opposite direction class. So we move from right to left. Okay, so from right to left. So started with the terms of frequency, slower frequency, and then highest frequency to the left. As you see here, we have AM, FM, TV, radar belongs to this band, and you see the corresponding wavelength: 1 centimeter, 1 meter, 100 meter, meaning this is the cycle, the wavelength. And here we have the infrared, ranging from this to this infrared band. Then we have a very small portion here. So this is what we call the visible light, where in terms of wavelength, we have 400 nanometer, 500 up to 700 nanometer. Okay, and then we have what we call ultraviolet, then followed by the X-rays. Okay, in terms of wavelength, from 0.01 nanometer to 10 nanometer. We have the gamma rays, and then to the leftmost of this is the cosmic rays. So increasing energy from left to right. The other one is from right to left. Okay, and another way to look at it. So we have here another illustration to give us more details. All right, so we have here what we call extremely low frequency ELF, very low frequency. Then we have the low frequency. And next here we have the medium frequency, the high frequency, very high frequency, extremely high frequency, and so on and so forth. So the frequency wavelength are here. So for this one, between this VLF and LF, 50 hertz. So in terms of wavelength, we have the 6,000 kilometers. That is the wavelength, meaning in one cycle. So it travels 6,000 kilometers. But for 1 megahertz, we have 300 meters, the wavelength, 500 megahertz, 60 centimeters, 1 gigahertz, 30 centimeters, 10 gigahertz, 3 centimeters, and 30 gigahertz, 10 millimeter, 600 terahertz, 500 nanometer, and 3 petahertz, 100 nanometer. Then 300 petahertz is 1 nanometer, and so on and so forth. Okay, so you see here, as the frequency increases, we can see that the wavelength becoming shorter and shorter. All right, so you can also see here the applications. So we have here safe and beneficial in appropriate dosage. Okay, so we have for transmission line, and then we have for television. These are the radio frequencies. So here, danger, no? For satellite, microwave. This belongs to non-ionizing, but this is dangerous already, the frequency here, high frequency. Then we have here safe and beneficial and appropriate dosage for sunlight. No? Sunlight, we have visible light. Then infrared here, infrared, 30 gigahertz. Then we have here ultraviolet. Then we have the X-ray, and then we have the gamma rays. So this is already very harmful, extremely harmful, this part here. Okay, so this is another way to look at the electromagnetic frequency spectrum. So this has more details than the other chart. Okay, so these are the details in terms of frequency and what are their applications. Like for example, for band number 2, 30 hertz to 300 hertz. So designations, that is the extremely low frequency. So what are the applications? It includes AC power distribution signals, that is 60 hertz, and low telemetry signals. Then for zero point 0.3 kilohertz to 3 kilohertz, that is for very low frequency, that is the voice frequencies. So it includes frequencies generally associated with human speech. Standard telephone channels have a 300 Hz to 3000 Hz bandwidth and are often called voice frequency or voice band frequencies. Then for 3 kHz to 30 kHz, that is very low frequency, includes upper end of the hearing range used for specialized government and military system like submarine communications. Then 30 kHz to 300 kHz low frequency used for marine and aeronautical navigations. Then zero point 0.3 MHz to 3 MHz, that is medium frequencies. This is used for commercial AM radio broadcasting, that is from 5335 kHz to 1605 or 1605 kHz. Then from 3 MHz to 30 MHz, that is for high frequencies, referred to short waves used in two-way radio communications, Voice of America and Radio Free Europe broadcast within the HF, high frequency band. Amateur radio and citizen band CB radios are also used signals in this range. Then 300 MHz to 30 MHz to 300 MHz, very high frequency, used for mobile radio, marine and aeronautical communications, commercial FM broadcasting. The commercial FM broadcasting ranges from 88 MHz to 108 MHz, and commercial TV broadcasting of channels 2 to 13, 54 MHz to 216 MHz. Then 9, we have 300 MHz to 3 GHz, that is ultra high frequency, used by commercial TV broadcasting of channels 14 to 83, land mobile communications services, cellular telephones, certain radar and navigation systems, and microwave and satellite radio systems. Frequencies above 1 GHz are considered microwave frequencies, which includes the upper of the UHF, ultra high frequency range. Then 3 GHz to 30 GHz SHF, that's super high frequency, used for microwave and satellite radio communication systems. 30 GHz to 300 GHz, extremely high frequency, seldom used for radio communication except in very sophisticated, expensive, and specialized applications. Then zero point 0.3 terahertz to 3 terahertz infrared. So that is the infrared frequency, not referred as radio waves. It refers to electromagnetic radiation, generally associated with heat, used in heat-seeking guidance systems, electronics photography, and astronomy. Then we have here T terahertz to 30 terahertz. That's still an infrared, so there's no designation yet. 30 terahertz to 300 terahertz infrared also, so still no applications. Then zero point 0.3 petahertz to 3 petahertz, that is visible light, includes electromagnetic frequencies that fall within the visible range of humans. Light wave communications is used with optical fiber system. Then 3 petahertz to 30 petahertz, that is for ultraviolet rays, X-rays, gamma rays, and cosmic rays have little applications to electronic communications. Okay, so I want to highlight here the three important frequency spectrum. That is the number 17, uh, 30 petahertz or 300 petahertz X-ray, that's used for X-ray. Then 18, we have zero point 0.3. Sorry, I forgot this A here. That is for gamma rays. Okay, and then for 3 to 30 E hertz, this is for cosmic rays. I'll get back to you for the meaning for E. All right, so here's the other presentation, the summary, no? The summary of the International Telecommunication Union ITU band designations. All right, so you have to remember this. These are very important class. Usually in the board examinations, there are problems that will really need your familiarity of this. Okay. The E, by the way, the E here is for exa, not exahertz. Exahertz. So remember that if you have, say, 1000, we have what we call kilohertz. Okay, so 1000, that means kilohertz. We're talking of frequency. So that is means kilohertz. If you have something like this, here above we have 3 zeros, for 6 zeros, so that is now M. We have what they call megahertz. Okay, then if you have 9 zeros, so that is what we call gigahertz. Okay, so this is gigahertz. Gigahertz. This is megahertz. And this is kilohertz. And if you have 12 zeros, when you have 12 zeros, so that is the terahertz. Okay, and if you have 15 zeros, so you have petahertz. And if you have 18 zeros, I think that's the exahertz. Okay, so you just continue this one class. So to write the number of zeros. Okay, so that's it for the electromagnetic frequency spectrum. Then let's talk about wavelength. So wavelength, it is the length that one cycle of an electromagnetic wave occupies in space. That is the distance between similar points in a repetitive wave. Like for example, if you have this signal, something like this. Okay, so that is one cycle, and then we have another something like that. Okay, so this is what we call wavelength. Wavelength, uh, the symbol used for wavelength is what we call lambda. Okay, that's lambda. So it is inversely proportional to the velocity of propagation. Okay, so in formula, wavelength is equal to velocity divided by frequency. or wavelength, which is lambda. So that is the, okay, I'll change this to avoid confusion. I write it properly. So this is, okay, so this is lambda. All right, so lambda is equal to c over f, where c is the velocity of light. That is 3,000 million billion, 300 million meters per second, or 3 times 10 to the 8 meters per second. All right, so f is the frequency in hertz. So the total electromagnetic wavelength spectrum showing the various surfaces within the band is shown in figure 1, dash 5. Okay, so here, this is the one that we have shown earlier in the electromagnetic frequency spectrum. So we have here some sample problems, class, to calculate. We have determined the corresponding wavelength ranges from the following ITU specified frequency bands. For example, medium frequency MF, ultra high frequency UHF, very high frequency BHF. So solution, so for medium frequency, as per ITU, ranges from 0.3 megahertz and up to 3 megahertz. So you just refer it here. Okay, so you just refer it here. Okay, so this is the one that is mentioned in the problem. That is medium frequencies. Right, so this is the frequency range, so use that information. Okay, okay, from there, so use the formula lambda is equal to c over f. So substituting, so at this lower range of the band, so we got this 1 kilometer. Then for lambda 2 at 3 megahertz, so you have 100 meters. So therefore the wavelength for the medium frequency are between 1000 meters and 100 meters. So that's the answer. For ultra high frequency, okay, so where is it? So you can see it from this table class, or you refer from the other frequency spectrum chart. Right, for B ultra high frequency, so same calculation, you just for the lower range, so ultra high frequency. So for ultra high frequency, where is the ultra high frequency? This one. So for ultra high frequency, so this is the range. Okay, so using that information, okay, so substituting, so we have 3 times 10 to the 8, the speed of the light, then 300 megahertz, so you get 1 meter. For lambda 2, so 36 hertz, lambda 2 at 36 hertz, 3 times 10 to the 8 divided by 300 times 10 to the 9, so we get it 100 centimeters. So therefore the wavelength range from for UHF is from 1 meter to 100 centimeters. So class, this is at not 36 but at 3 gigahertz. Once you look at here, 3 gigahertz. So this should be 3 giga. This is not 6 but G. 3 gigahertz. Okay, so at 3 gigahertz, so you have here 3 times 10 to the 8, and 300. So 3 gigahertz is the same as 300 times 10 to the 9. Okay, so therefore the wavelength range for UHF is from 1 meter to 100 centimeter. Okay, so for C is 300 megahertz, very high frequency. So for very high frequency, this one. So very high frequency, we have 30 megahertz to 300 megahertz. So use that value. So we can calculate uh, 30 megahertz. So we have 3 times 10 to the 8, that is the speed of light. 30 times 10 to the 6, that is the lower range. So you get 10 meters. And for the second one, for the upper range, so we have 300 megahertz. So again, substituting. So we get 1 meter. So therefore, the wavelengths for VHFs lie between 10 meter and 1 meter. So equation 19 can be used to determine the wavelength in inches. Okay, so we can also calculate it using an inches class. So lambda over. Alright, but normally we use this using the unit of meters, no? Because the speed of light is 3 times 10 to the 8 meters per second. But wavelength can also be done in inches if the given is in inches. So in inches, so you have to use this um, value for C, 11.8 times 10 to the 9 inches per second. Okay, so if the result, the wanted result is in inches. Okay, or just simply convert this to inches. Okay, then we have the bandwidth. So bandwidth of an information signal is simply the difference between the highest and lowest frequencies contained in the information. So bandwidth of a communication channel is the difference between the highest and lowest frequencies that the channel will allow to pass through it, that is its passband. So for example, for FM, so as shown briefly a while ago, for FM the range is from 88, right, from 88 megahertz 88 megahertz to 108 megahertz. Okay, so the range is 88 to 108. Now if you're asked to calculate the bandwidth, so as mentioned in this slide, so the difference, just the difference. So what you're going to do, you just subtract, no? So the bandwidth, therefore, bandwidth or BW is just the difference of the upper band and the lower band. So 108 minus 88, of course that's megahertz. So this is 20, right? 20 megahertz. So that's the bandwidth for FM. Okay, so I hope you have understood this one. So bandwidth of the communication channel, it must be large enough to pass all significant information frequencies. It must be equal to or greater than the bandwidth of the information. A communication channel cannot propagate a signal that contains a frequency that is changing at a rate greater than the bandwidth of the channel. So it should be equal to, or the bandwidth should be equal to or greater than the bandwidth of the channel. Alright, so I think that's all for this discussion class. So to know more about the details of our discussion, so you go to this slide. Originally, that slide is taken from this link, and other informations were taken from these different sources. Okay, so thank you very much and hope to see you again in our next lecture. So bye for now. See you again in our next video. Bye.